Hello, everyone. Welcome to the broadcast today. A little bit different broadcast than normal today. Normally, we do a deep dive on a particular SageMaker built-in algorithm. Today's a little bit special. We're breaking from the norm, and we have a couple of special guests, so you don't have the same presenters as normal. My name is Chris Burns. If you've been on any of the broadcasts in the past or have worked with us at any length of time, hopefully you recognize the name. I'm a solutions architect here focusing on AI and ML partners. And of course, just a reminder, this is a special series just for you ML partners. You have the competency, so you get these special broadcasts to help you along down your path of machine learning. So with me today, I apologize in advance if I get the pronunciations incorrect, but I have Simon Corsten Oliver, a senior ML scientist, and I also have Thomas Delte, applied scientist. And what we're going to talk about today is more of a scenario rather than a single algorithm. It's a pipeline, if you will, and it's going to deal with pulling OCR off of pages that are a combination of handwritten as well as typed text. So when we talk about OCR, it's sort of old school to talk about OCR, but to do it very well is still very, very difficult. And to do it well with a combination of dense text and sparse text and handwritten text and typed text is still quite a challenge. So today, like I said, it's a scenario. This is an experimental scenario. So just to set expectations, I want to make sure you don't understand this is not something that's a pre-built service from AWS that you can just go and use. This is really a demonstration of how to pipeline some algorithms into a nice process. And so what we're going to learn about today, we're going to learn about some CNNs for page segmentation. We're going to learn about some SSDs, single shot multi-box for line detection, and then a very clever use of CNN-BILSTM. So that's a bi-directional LSTM for handwritten text recognition. I don't want to spend too much more of your time. I want to get this over to Thomas and Simon so they can get to the good stuff. As usual, if you have any questions, please put those into the questions box, and I'll be monitoring that, and I'll try to splice those into the presentation when it's appropriate. And so with that, Thomas and Simon, I will hand it over to you.
Thank you. My name is Thomas, and I'm going to present you the work that I've been collaborating on with an intern we had this summer, the PhD candidate from the University of Toronto, Jonathan Chung. And the problem we asked him to work on, and that's a problem that was brought by some of our customers, specifically working with SageMaker, is how can you extract text from handwritten documents. So if you look at this kind of documents here, these are typically, you have a lot of forms in the banking industry, in the healthcare industry, in the law industry. Lots of data has been scanned and digitized, but inside the handwritten text has not been able to be extracted in a proper fashion to be indexed and searchable and reused. So we looked at this problem, and we thought, how can we solve that? So first thing we did was to gather a data set. For handwritten text recognition, the world recognized data set is called the IAM handwritten database. It's made of 657 different writers, more than 1,500 pages of scanned text. And what's really interesting is each of these pages have been segmented at the form level. So we get a bounding box around the forms, we get bounding box around the lines, and we get bounding box around the words themselves. Right, so you can really build algorithm at any level that you want. What's really interesting about this data set, in my opinion, is how many writers you have, because recognizing like the handwritten text of a single writer is not such a complicated task. What's hard is to generalize at all the different ways people use. Some people use cursive, people use script, people use a combination of the two. So really the difficulty lies in being able to develop an algorithm that capture this variety of handwritings. To make sure it's precise here, when we split our training and our testing data, we split that by writer, right? So all the writers from the testing set have never been encountered in the training set. Okay, so tell you a bit more about the solution we thought about. So we thought instead of we try to break down the problem into a series of different individual, easier to solve problems. The first one was how can we detect handwritten blobs? So first, in a form, the objective was to find a single paragraph of text. That's going to be the first part of the talk, and I tell you how we solve that. So in the second part, given a paragraph, we want to segment and get individual lines. And that's necessary because of how we built our character recognition algorithm, and we cannot have two lines, one on top of each other. So we first have to segment either by line or by word. Once we've done that and we get the line segmented, then we can do handwriting recognition. And then we have a mapping from line to line, and then we can bring that back if we want, back to the original input image to have proper mapping of the text on the form to the one we recognized. And in this handwriting recognition is really made of two parts. One is to recognize the most likely characters, but quite often that's not enough, because the most likely character is not always the right character. I'll show you a few examples, but sometimes you could swear, taking alone, that a letter, for example, is a U, but really it's an N, and only makes sense in context. So you need a language model to correct the errors that your character recognition algorithm has done. So we're going to see how we can build this end-to-end pipeline using MXNet, and specifically we use Gluon. Just a point to all the code of all these experiments I'm going to talk about is available online in a GitHub repo, and I'll show the link in a few slides. Also, we have pre-trained models for each of these steps. So you're really able, if you want to just pick, there is one notebook that does really end-to-end inference from the form all the way to the text. And you're very much welcome to try that yourself. And we made the pre-trained models available as well. So the first part, any questions so far? Okay, so the first part, page segmentation. So maybe this part is the one that's really kind of tailored to the IAM dataset. So that's the one that's slightly less applicable in a generalized manner. But if you see how we do line segmentation, that's something you could apply in a more general type of form. So that was also the first task we gave to Jonathan as he was ramping up with the use of MXNet, coming from a PyTorch background. And if I can quote one of his comments was, he was surprised how easy and how nice it was to work with MXNet Gluon. And it took him maybe a day to ramp up and be up to speed on the API of MXNet. So why I say that it's kind of tailored to this task is because all these forms coming from the IAM database are structured in the same manner. There is a written text at the top, and then you have the handwritten transcript below it. So it's not a multi-object detection, it's a single object detection. We tried two approaches. The first one, we really, when we tried to solve this problem, this was less of a research approach we wanted to take. We wanted to solve the problem. So we were not like trying to use the most cutting edge solutions. We wanted to find the state of the art, the best solution that would get us to the solution the fastest. So we tried first a deterministic approach using maximally stable extremal regions. So that's a purely deterministic approach. It's available using OpenCV. You can very easily develop this algorithm. The idea is quite simple. You first detect blobs, and you make rectangle around them, and you can use blob detection from OpenCV. And then you add, you have a hyperparameters, delta, by which you increase the boundary of these blobs. And then you look at the overlap between these regions. And if you have an overlap greater than a specific hyperparameter, then you merge the blobs. And then it's an iterative process. And you can see it's actually decently good at capturing regions on the page. But we had two issues with this approach. The first one was, for every form, we could find a set of hyperparameters that would give us a perfect result. However, each of these hyperparameters were different from one form to another. So we couldn't have, it wasn't like a single solution we could apply with 100% accuracy. So the second issue was time. It would, on a normal machine, it would take maybe like 10 seconds to find all the bobs. So not something we could apply in real time for training. So we decided to take a second approach using a convolutional neural network. And really, since we knew we were only doing single object detection, what we are trying to predict were 4 values. The top left corner, made of X and Y coordinates, and then the width and the height of the box around the text we want to detect. So for that, we took a relatively simple CNN approach, some convolutional layer, some pooling, but not too much because we don't want to lose too much of the spatial resolution, because here we had a problem that was extremely spatially correlated. We knew we wanted the box was kind of always at the same area in our forms, and then some fully connected layers, and then these last 4 hidden units, each of them with a sigmoid output. We're predicting between 0 and 1 because our coordinates are like relative, right? So 1 would mean at the bottom or the right, and 0 would be at the top left corner. And same for width and height, relative to the total size of the image. And so I thought that was a pretty simple problem. We had very good training data, and I thought it would work straight away. And we found that we had difficulty to reach good accuracy on the testing set. The reason was the data set was a bit too uniform. So what we did was adding some data augmentation. So I don't know if you can see here, but we shifted the forms a bit up and down, adding some padding left and right, just to make the values slightly less predictable, slightly less the same. So the top left corner is not always at the same position. And this increased a lot the accuracy. And another technique we used was to first trying to minimize the mean square error for all these values. And when we reach a good enough overlap, then we can fine-tune using the IOU, which is the intersection of a union. And why we don't do that at the very beginning? Because at the very beginning, you might not have any intersection, and then you would have just consistently 0 for your IOU. So if we look at the results, I don't know if you can see that clearly, but the algorithm after a few 100 epochs learns really well, and effectively, if we look at the qualitative analysis of the results, we managed to capture every box. Why it's important? And when you take a pipeline approach, and I think it's true for not just OCR, but any kind of pipeline approach you do for machine learning, is you need to be extremely careful, because each step introduces a loss that cannot be recovered in any further step. So for example, here, if you do a bad cropping of your form, then it's data that you will never be able to analyze later. So for each of these preliminary pre-processing steps, we really strive to get 100% accuracy, because there's seemingly simple problems, but you really want to have your loss on the character recognition, not on the text cropping. So it's very important to have very robust algorithm there. So any question on the page segmentation part?
We do have one question, Thomas.
Yep.
The question was, the pages appear to come all in landscape orientation, if you will. I'm sorry,
Yeah.
not landscape, but portrait. If they were to come in landscape or rotated, how does the algorithm treat the text?
So in that case, the issue you might have is you could have a shape mismatching between for your deep neural networks. So let's say you're using a hybridized version of your model, then you expect the input data to be in a specific shape. So if you rotate it and you don't like rotate back the image into the same dimension, that would be your first issue. But it's not unsurmountable. It's not an insurmountable issue. You could, for example, rotate back your landscape to portrait, and then probably you couldn't use like straight away the same pre-trained model. But if you had enough training data that was both in portrait and landscape, then I assume it would work very well. The alternative is to pad your data to be square. So you add some white or black at the bottom and the top, or if it's in a landscape, if it's in a portrait, the left and the right, and you get square input, and that way you have you don't need to rotate your data, and your algorithm can pick up features that are consistently in the same orientation. Because the issue when you rotate is then the features are going to be rotated as well. That makes sense?
Yes, I believe it does. Thank you.
Okay, so the next step, once we have our forms that have been extracted, so we have pure handwritten text at that point, then we can do line segmentation. So input is an image containing only handwritten text, and output is a bunch of bounding boxes for each handwritten line. So that's we're in the realm of multiple object detection. And here we tried two approaches. The first one was using SSD, so single shot multi-box detector. So the M is missing from the name, but that's how it's called. And using SSD for words directly. So the single shot multi-box detector, we took the base implementation that's available in Gluon CV. So Gluon CV, it's a Gluon computer vision. It's a computer vision toolkit available for MXNet. It comes with several pre-trained and non-pre-trained algorithms for object detection, image segmentation, and intent segmentation. In our case, we took the SSD implementation for object segmentation. And we customized a few steps. First, the data augmentation. We used a data augmentation that's specific to our task, and I'll speak about that in a minute. We used different default anchor boxes. So anchor boxes incorporate prior in your model. So if you have a prior on what the object looks like, that's where you put it. We changed the network architecture again to fit better our problem. And we tweaked the NMS, non-maximum suppression thresholds to get better results. And that's a combination of all this tweaking that really get us really good results. Because the base, so maybe there is a lesson here, which is sometimes you find pre-trained model or you find pre-trained, pre-made architectures, and you don't get good results. I guess the learning for us was keep tweaking and incorporate problem-specific changes to get better results. So I said we used specific data augmentation. Effectively, what we did was take some lines and remove them. So you see here, we remove that one, here we remove that one. It was just for to make sure the algorithm doesn't expect always to have all the lines one after each other, because we have some cases where it's not the case. Maybe some people leave some space in between a few lines. So it's important to add a bit more noise in the training data to avoid overfitting. For the anchor boxes, SSD, how it works, so I'll have a slide just after that. That's going to go in more details. So think about for every pixel of feature maps, when you have your featurized representation of your images, you're gonna try to predict whether you have a given object, and what you're trying to predict with SSD is you're trying to predict from a input prior anchor box, like one of these. You're going to try to predict how much you need to shift the box in X and Y, and how much you need to shift the width and the height. And why all that makes sense is because you have also a loss that's trying to minimize this shifting you're doing. So that's why the prior is important, because each anchor box is going to try to still kind of stick to the prior, but do the necessary modification to get the best prediction. Right? So if we look at this example, you have two objects we're trying to detect, and here it's going to be easier for example, this anchor box here, this prior anchor box, to move to be that one, and this one are going to be easier to move to be that one than shifting that one to be the dog, for example, because of this loss that's penalized by how much you changing a prior anchor box. And you have thousands of them. So typical images here, 17,000 anchor boxes. That each of them, what they do is they predict 5 things. They predict the delta in X and Y, the delta in width and height, and the class that this box should be, right? So when I say 5, really when you look at the implementation, it's 4 plus n as n the number of classes. So each of your class gets a specific value, and then you apply softmax, and then you get a distribution probability over the classes that this anchor box is supposed to capture. Okay, so if we look at the network architecture, we get our image. We take ResNet 34, which we found was a good compromise. It's a pre-trained model on ImageNet, so it's a data set made of 1 million images with 1,000 different classes. We use it pre-trained because it has already learned to capture all the features, all the patterns that are important to detect when you're doing object detection and image classification. And we remove the first layer. Why we do that? So it's again, speaking of shape mismatch, so this one is not in width and height. It's a mismatch in depth. So ResNet 34 was trained with RGB images. RGB images makes that the first layer, your first convolutional layer, will have convolutional kernels which have 3 dimensions, which have on the depth dimension number 3. So 1 for each of your input layer. So 1 kernel for R, 1 kernel for G, 1 kernel for B. In our case, we have grayscale image. So grayscale image is only a depth of 1, so only values between 0 and 1 on the grayscale. So here, when you have this problem, you have a few ways to solve it. You could just duplicate your grayscale value on the 3 RGB channel. So you're back with an RGB image, which is basically 3 times the same grayscale image. And in RGB representation, you actually get the grayscale image, but that's using more memory. The alternative is to look at the first layer, and what you can do is either pick only one of the channels for your filters. So you can pick, for example, the kernels on the green channel, or the red channel, or the blue channel. Or what you can do alternatively is to just take the average of each of these kernels and get, if you want, grayscale kernels. So we tried these 3 approaches. What we found was roughly the same performance. However, to us, it made more sense to take the average of the kernels, and so we don't use extra memory to move the input to RGB. So that's what we did. So we took the pre-trained first layer, and then we averaged the kernels across the depth dimension. So we're left with grayscale kernels for convolution. Then after the first pass of ResNet, we're left with feature maps that represent the featurized version of our image. One thing we've seen is people have different size of handwritings. Some people write like with big letters, some people write with small letters. So to solve this issue, and that's actually part of SSD, like the SSD paper in the implementation, we use different scales. So we have some dense sampling steps where we're gonna reduce the spatial resolution of our feature maps. And at each step, we do a bounding box prediction and category prediction for each of our anchor boxes. So the downsampler is relatively simple. We are just doing some convolutions and then some max pooling. So they divide the resolution by 2. And for the category CNN, what we do is slightly different than what you're used to. Like usually classification is done through fully connected layer. But if you do convolution with a certain number of output channel, and this number, for example, corresponds to your number of classes, then you can see each of the convolutional operation on your feature maps as a prediction of belonging to this given class on this specific area of your feature map. So that's what we do. And in our case, the number of classes is 1. It's either a line or it's not a line, right? So this gives us a bunch of bounding box that have, we have a threshold where you say, okay, it's over 0.5, this bounding box with this shift in X and Y and width and height is a good candidate, and it probably contains a line. But remember, we start with almost 17,000 bounding boxes, and lots of bounding boxes are going to end up like around the same area, all predicting that this is a line. So what you need to do is to do merge this bounding box. Merge them or look at which one are actually slightly higher than the other with a big overlap. So simply put, you look if there is an overlap and the overlap is big enough, you kind of keep the one that has the highest prediction value. And this threshold that you're using can be tweaked. And from the left to the right, you can see when you don't put the non-maximum suppression, so you can see lots of different prediction around the same areas, and then when you do non-maximum suppression, so a lot cleaner output. So again, here you can see that's this visualization, and I'll show you afterwards, is built with MXBoard. MXBoard, it's a MXNet plugin for TensorBoard. So you can plot images, losses, audio, whatever, all your different metrics, you can plot them in TensorBoard using MXBoard. So that's how we got that. And you can see the algorithm is slowly learning to capture the lines. So if we look at the result and the IOU, we got around 0.6, which is pretty good. And in almost every cases, we got the line in a good enough fashion that we could do the optical character recognition. But we had a few failure cases, like for example, this one. You can see that because of how the non-maximum suppression works and it looks at overlaps, we ended up sometimes with like 2 regions like almost touching each other. And if you remember what I said about pipelining, you know, like this line, we know that we'll never recognize it because we're splitting it in 2, and then it would really mess up our pipeline. So even though we had maybe 98, 99% of the cases, it would work well enough, and it wasn't good enough for us. So we tried a different approach. And that approach was a mix of deterministic and deep learning approach. So we use the exact same algorithm as detecting for lines, and we use that to detect words. And then we used a simple deterministic algorithm to create the lines. And the algorithm was, look at my box, is there another box on the right? If there is, then you kind of incorporate it in the line, and so on and so forth. And you continue like that. And it's very fast because you're only iterating over bounding boxes, and you at most have like 50 of them or 100. And the results were extremely good. So after that, we managed to capture every line of our forms. So now we're left with well-defined lines of handwritten text, and we're going to move to handwriting recognition. But is there any question beforehand?
We do have a question, Thomas.
Yep.
One was the language specifically trained for this scenario is most likely English. But
Yes.
what are the implications of training against different languages?
So right now, until we reach that point, I would say very little for most Latin languages. Then I'm not a linguist,
Sorry, I hate to turn my
and Simon is a linguist here, but I know some, basically some languages you might learn line, the concept of line might make less sense. You might read from top to bottom, right to left, and so on and so forth. So you might need to have some language specific training data. But for most languages so far, that works in a line fashion. And here we're not even talking left to right or right to left because it doesn't really matter for us. Then that would work. But when we come to the character recognition, and I'm going to speak to that in a bit, and if you want, I'll add something onto the implication of working with different vocabularies and different alphabets, then yes, it would change quite a few stuff.
Great, thank you.
So when you come to handwriting recognition, you get as input an image of a single line of handwritten text, and what you want here, there is a concept of time step. So let me explain what the time step here. So we look at the image as a time, in quotes, aligned data. So they're aligned in that case left to right. So if we sliced the input image in n slices, let's say 50, then when I say time step, I mean one of these vertical slice. Okay. We're gonna pass all these slices through our handwriting detection model. For each of these slices, we're gonna predict what character this slice might be. And character could be just the empty character, like no character. And the output will be a probability distribution over the alphabet. And here, that's where it matters. So I think for the English, so there was English text, we use like uppercase, lowercase, and a bunch of special characters. So what you need to be careful here, for example, if you are trying to translate, to do the same with Chinese, is your vocabulary of characters is extremely a lot larger, right? Like you would have thousands of these characters, and maybe the approach wouldn't work that well because you wouldn't have as many. You would have a very imbalanced data sets. Whilst here, in that case, it's a lot easier to control how balanced your data set is, because we're only speaking of like 60 characters. If you work with a language that has a lot of accents as well, you might have a very large vocabulary as well. So maybe you could look at different approaches where you're trying to predict a letter and then maybe an accent at the same time. So English is maybe indeed one of the easiest one to apply this this technique on, and the one that most likely works the best. So traditionally, we base our approach on a paper that's using CNN and BILSTM. The idea is to first do a pass with a convolutional neural networks that we extract features from our images. So we start with a grayscale image, and then we end up with a bunch of feature maps that have inside the extracted features of the image, that then we slice that in vertical slices like that, each of them being like a time step. Again, I say time, but that's because our data or signal is aligned from left to right, because we're reading like left to right, so we can be like it's a time step. And we pass that through LSTM, by LSTM, so left to right and right to left. Yeah, so these arrows are inaccurate because you should also show that it goes on the other side. And then for each time step, you get the hidden state of your LSTM. These hidden states, you pass them through a fully connected layer that has as many hidden units as you have characters. So for example, here, the hidden units for M would give you 80% probability that the first time step belongs to the M character. So we went a bit further. We had this issue where some lines, and if you're trying to align against same dimensions, and you need to stretch some lines and some others less, so you end up with different scales of handwriting. And just some people write bigger, some people write smaller. So we took a trick from the SSD book, I would say. So we added a downsampling step from the ResNet feature extracting step, where we had some image features that we passed through by LSTM, and then we also did another downsampling step where we reduced again the size of our feature maps, and a different LSTM was used. And then the hidden step for each time step is concatenated. So each time step in the end is represented as a concatenation of the hidden state of the LSTM at two different scales. So I would say when you have problems when you're doing object detection or even image classification and different things like that, that's always good to have this downsampling step or taking features at different scales. It really helps your network to be able to reuse this information, basically. So we and then, like I said, you have your hidden states, and this orange stuff represents a fully connected layer where each is a character, and in that case we can see, for example, the first time step highest probability is 0.23. Okay, so now you might think, okay, speaking about time steps, and you said hundreds of them, and you predict H, but then maybe H is over 2 or 3 time steps. Well, how do you do that, right? How do you align your label with your input? So that's the big issue in our case. We don't want to split our image in 100 slices and then manually go and say, hey, that's nothing, H, E, L, oh, actually it's a double L, and so on and so forth. So that's where the CTC loss comes in. So that's a problem where when you want to do alignment of sequences, and you don't have the real alignment, you just, it comes with a few constraints. For example, it's a monotonic many to one, which means your inputs, the alignment in our case is left to right, needs to be aligned with your outputs in the same order. So that's the kind of the monotonic idea. It's growing in the same direction. So you couldn't have hello written here and try to predict whole, right? It wouldn't work with a CTC. Also, it's many to one, which means you need more inputs than outputs. Okay. However, despite these constraints, is extremely powerful because you don't need to do alignment. It all automatically learns the alignments of your input and your output. And how it does is it defines a collapsing function. So each of your time step, each of these slices going to be predicted, like I said, H, E, nothing, L, nothing, L, 0, 0. And this nothing is actually a special character. It's necessary because, for example, when you have like double the same token, the double L, well, you need to distinguish that between H, right? So the collapsing function says if you have repeated characters, then they collapse to a single character. If you have repeated character but separated it by the empty character symbol, then they collapse to two different characters, right? It's like a stop, and then you start again. So this has practical implication. For example, when you're deciding how many slices you should slice your input, because that's something you decide, you need to take into account that you need, for example, for double L, to be able to correctly predict double L, you need at least 3 slices, right? 1 L, 1 stop character, and 1 L. And the last bit of the collapsing function is if you change character, then it's as if you had a stop in between, right? So it's going to be L and then O. So that's how the CTC collapsing function works. And if you look at how we can train a model, so the beauty of the CTC is that it's differentiable. Because when you train your model and you want to detect hello, you have the ground truth, the hello string, and then you want to, if you use, for example, the cross entropy loss, you want to look at the probability of predicting hello. So you don't need to care about because obviously if you think at the probability for each slice predicts over the entire alphabet, a distribution probability, and then the next slice as well, So it's untractable if you try to compute the exact probability for each string that can be predicted with this algorithm. It's completely intractable. It goes into the 30 to the power of 80 or something like that. It's not doable. But we are only interested in the probability of predicting the correct label. So the correct label, there is only a finite amount of ways to get to the correct label, right? So you might have H, E, E, L, O, right? And how the CTC algorithm works, CTC stands for connectionist temporal, classification loss, is you don't actually try to go through the entire tree every time. It's saving the intermediate values of the probabilities for each of the steps. So in the end, it is called dynamic programming. It's using dynamic programming in order to make the computation a lot more efficient. And if you look at the actual operation you're doing to get this final prediction accuracy for the right label, it's only sums and multiplication, right? The probability of this one multiplied by the probability of this one plus this one, and so on and so forth. So it's differentiable because it's only multiplication and addition. And if it's differentiable, it means you can then tweak the weights of your network according to the gradient of the loss. With so you get the gradient with respect of the loss, the CTC loss you computed, and you modify then your algorithm to minimize that loss, and so on and so forth. So you can train it with a stochastic gradient descent, and that makes it extremely efficient to train. So that was for training. Training is easy. We know the correct label, and that's what we try to get the probability of predicting the correct label. But for inference, we are stuck because we don't know the correct label. And if we wanted to get the real probability for each of the possible label, like I said, it's intractable. So then you have different approaches to that. The simplest one is a greedy approach, or the best path approach. But that can lead you to some kind of weird situation. Just take this example. You have an alphabet made of A, B, and the empty character. And let's say for the first time slice, we predict 0.4 for A and 0.6 for the empty character. For the second time slice, we predict 0.4 for A and 0.6 for the empty character. So if we take the greedy approach, then, okay, first time slice, we say it's most likely to be an empty character. Second time slice is most likely to be an empty character. Then the probability of the, actually, so the result of empty character and empty character is empty string. So if total probability is 0.6 and 0.6, it's 0.36. However, if we look at the paths that say A followed by empty character, or A followed, or empty character followed by A followed by A, which all resolve to the string A, and we sum these probabilities, we get 0.64. So the greedy approach, where we take just for each time slice a maximum value, doesn't always give you the correct highest probability of the final label. So you need like a heuristic or a technique that will give you a balance between checking every path in the tree to get the real probabilities and the one that just takes the greedy approach of the highest probability of each time slice. And the answer to that problem is beam search. So beam search, what it does is you keep a certain amount of best candidates, and then you go from each best candidate state to the next state. You look at what is possible, and you update the probability of your best candidates. So when you use the CTC laws, the problem is, like I said, there is a collapsing function. So for example, if you have A and then followed by A, you're not going to get the string AA. You still get the same string A, because two characters of two time slice that have the same predicted characters, like we said, we collapse them into a single character. So it's very similar. Each time step, we look at the extensions. We look at how this extension collapse into strings. We sum the probability of these same strings and so on and so forth. Right, so this gives us, in our case, we use like 20 candidates, and it gives us a kind of good approximation of the best, most probable labels. Okay, so that was one thing. The next thing we can think of, because now we have our predicted tokens, people don't write very well. So some characters might be off and might really look like a different one. So that's where we want to have the language modeling come into play. And the simplest language modeling you can do is you can just try to do some spell checking. So you look at the closest word. So we used an out-of-the-shelf like word correction from I think NLTK or Spacey, and you look at the edit distance, how many insertion, addition, or swap you need to do in order to get to a correct word, and that's what you use as a weight to score like proposals. However, we found that this actually gave us worse result than the pure OCR. What worked really well is to weight each type of insertion, deletion, or swap by how similar letters are. For example, like I said, U and N, people tend to write them very similarly, or O and A, they look very similar, so they have a lower weight. And this was the weight were computed by doing a first trying to align the prediction of the OCR with the real label and look at which character were a mismatch, and that's what we used. If I go very quickly, because I think we're maybe running a bit out of time, we get the output, we decontract the text, which means, for example, we replace don't with do not. Tokenize these words that we have predicted. Look at each suggested word, and for each suggested word, we take the minimum, the one with the minimum is distance, with the distance, like I said, weighted by how similar the letters we're swapping are. And then we detokenize, so it means we reconstruct the words that we had. So that was for the first approach, kind of slightly deterministic approach. And the second one you can do is use a language model. So a language model, typically what it does is you give context, usually left context, and you say, given this strings, this list of words, what is the distribution probability of the next word over the entire vocabulary? So, for example, if you say, I am swimming in the, it could be, it's highly likely that it's like swimming pool or in the sea or in the lake, but it's unlikely that you say table, right? You're not swimming in the table. So we use a language model in order to score each of our proposal. And how it works is using a measure called perplexity. And the perplexity, do we have here now? Perplexity is a measure of how likely a given sentence here is given a language model. So let's say you train your language model on the billion word corpus from Google, where you have like millions and millions of sentences, and you're gonna give a bunch of your proposed sentences, and the algorithm is gonna tell you, well, this one, because maybe some words are similar, they make sense, but they don't make sense in this context. So that's a way to capture the context of the entire sentence you're trying to predict. And that's how we rank the proposals. So now let me give you a few sample. I don't know if you can read from there, but we had this sentence, which sometimes is very hard to read actually. The dataset got all these lovely things. She waved a, or you can see the person actually wrote Tovely, or maybe made a mistake, and they kind of scratched it. And then when you do the lexicon search output, you got these lovely things, she waved a. And then when you add the beam search plus the lexicon search and the language model, you get got all these lovely things, she waved a. So, you know, you can see it's actually pretty good. And we looked at the character error rate, and every time we added you have the greedy search give you 18.9, and you add lexicon search, you go down a little bit, and then when you add the beam search, you go down again a bit more. So it's pretty good. It's still not perfect. You can see sometimes where, for example, the beam search makes it worse rather than better. For example, the sorry, with my, so this one has come for him to be taken seriously. So I said one way has been fixed, but if you see here, self as a stranger in this park, and it doesn't find the parks. But again, the handwriting is not so good. So I'm going to show you. I'm going to show you quickly a little bit of code and a little bit of results. So first, let me show you the results. So this is MXBoard. MXBoard, like I said, is a plugin for TensorBoard where you can put your data. And here I trained the optical character recognition part of the algorithm. And you can see the loss. So the training loss keeps going down, and then at some point the testing loss kind of stagnates. And if we look at the, we can have images, and here we have the test images, and I'll zoom in a bit. So you can see the test results are pretty good. Like together, you see like together was predicted correctly. The Porter brought, here we can see a issue where he didn't get the space between no and matter. but it got no matter how one might, so that's pretty good. And remember that all these writers have never been seen by the algorithm. So it's we segregate writers between training and testing set. And that's the training data, which is actually a lot better, but it will be so here heartily. I think it's heartily, but you can see here the algorithm got it wrong, right? So it's not perfect, but you're definitely in a place where you can start using that for indexing your data, and you will get like most of the word out, but it's not yet perfect transcription. And if we look at the code, I don't know how many of you are familiar with MXNet, so I'll go light on some parts. One thing that Jonathan did that's really useful if you're interested in OCR is he created a IAM dataset, and it's a base class dataset. Is a base construct in Gluon. That's so you can use it very easily, and you can request like the forms, you can request the lines, you can request the words. You can use it, and for example, straight away you get this, and then this notebook that's available in this in my repo, in my GitHub repo. You can go to Handwritten Text Recognition MXNet. The one I'm showing here is a end-to-end pipeline. So I'll quickly go over that one, where you see it's segmenting the text. Then here's the step where you're segmenting the words, and from the words you get the lines, and then from the lines you then do the language modeling. The entire pipeline that I described is here, so you can just read the code. The next, for example, here you can see that the perplexity I was talking about. So I want more eggs. That's 7,000 in the complexity score. And I want more constitutional, which doesn't really make sense, is 30,000. And if you just put a bunch of random words, and you're really above these baselines, you're like in the millions. And the perplexity it's a normalized matrix, so it doesn't get more as your sentence gets longer. So for example, here you're in love when you cannot fall asleep. It's kind of it's quite a likely sequence of words, so you see the perplexity is still even lower, that I want more eggs. So if we look at some of the qualitative results, if we look after the language modeling, so that's the entire pipeline. This one, okay. Ever been out in a submarine? I'll give you the spin around on these days. If you like, you could write it up. Boulay made face. You're still not exactly there, and we still have some work to do on the language modeling, but I think it's usable in an indexing context. So on the training part, I guess what I want to show you is how easily you can do the training in Gluon. So given a data loader, which has been built with our dataset, you pass the data in the context, in that case the GPU. You pass the label in the GPU. Under the autograd scope, you record what's happening, which means you're going to get automatic differentiation. And like we said, the loss is differentiable, so that's going to be taken care of for us. So we get the outputs of our network. So that's the entire step from the CNN-BILSTM and then classification for each of our time slice. We compute the loss. We do a backward pass, which is going to compute the gradient effectively. And then we update the weights according to this gradient we just calculated. Then that's all some logic to send some data to MX board in order to get the visualization I showed you just before. And then we just keep track of our loss and keep track of our epoch loss. And that's the training loop. And you run that, and then you can monitor the training there. It's a very good workflow, and the ability to put images, you're really seeing whether or not your network is training. So we found this combination of taking the time, basically if I have an advice or conclusion here to give you in terms of how we train that, is take the time to put together the proper metrics in order to be able to take action quickly. You don't need to wait that your network is fully trained. If you see that it's not training, that it's only predicting empty characters, then you know you need to switch something. So one lesson is make sure that you track your training, how it's learning, what it's learning, and use that to iterate quickly among different hypotheses. Because what I'm showing you here is the result of a lot of trial and error. We had different hypotheses. How many downsampling do we need to do? And for that, it's very important to do hyperparameter searches, where you try different ranges of parameters, or you can use a SageMaker hyperparameter search as well with like Gaussian processes, and makes it even easier. So yeah, so that's what I wanted to show you. The code is entirely available. Feel free to play with it, and if you have any issues, reach out to me, create an issue on the repo, and get engaged in the MXNet community as well. So there is a Discuss forum, and you're more than welcome to post your question there. I guess you already know about Amazon SageMaker, and check out the docs, and feel free to, if you have MXNet specific question, to contact mxnet-info@amazon.com. So we'll be very much happy to get in touch with you and help you with your MXNet troubles. So thank you very much. It was a pleasure to be there this morning. And if you want to follow up, that's my email address. Feel free to send me emails. And if you have any question, I think we still have a bit of time to take some now. Thank you.
Yeah, thanks, Thomas. We do have a couple of questions that came in. One question, pretty straightforward. How long was the initial training? So when you had the IAM data set, what was the what did that look like?
So how long does it take to train? Well, we're kind of lucky here at Amazon. We're training on NVIDIA V100s. So I believe the training for the last part is it's less than an hour. It's 30 minutes maybe to run 120 epochs.
Okay, great. And then another question was going back to the very first portion of the pipeline where the CNN was used. The question was, what sort of features are extracted from that? Is it just pixel data?
Is it just what?
Pixel data. So I'm not entirely certain.
So okay, so that's something actually. That's a very good point. In a talk I gave a few months ago in Macau, lots of people were struggling with the term features, and I can really understand why it's confusing. So features, what they are, effectively what they are, it's a values, float values, and they are it's like a tensor. If what they are, it's a tensor with a different depth that has float values, and these float values, they are used, they're not humanly understandable, but they're used as signal by your network in order to do prediction later. So you can see them as activations. So it's some signal that activated some part of the network, resulted on some higher values in some parts of the feature maps. If you look at the features at the very beginning of a CNN, you will notice that you learn kind of low-level features that are easily explainable. For example, you would see edge detection, right? So edge detection, sharpening filters, your network automatically learns these specific filters that result in inversion of your image, which is humanly understandable. But the lower you go in the network, the more filters you apply that combines information across filters, across feature maps, and typically less and less you can actually understand what is, as a human, what is in the feature maps if you try to look at the values. But your network learns what kind of combination, what kind of correlation of activation create specific signal that would make it more likely, for example, to predict H rather than J.
So we can speak about it intuitively, right? So intuitively, the networks learn about straight lines and curvy bits and like horizontal lines. Yeah, like you can see that it's figuring out how to piece all of those things together, all of the little pieces that help you to recognize each character.
Yeah, so exactly. I mean, that's Simon's right. That's the intuition. That's how you can think about it. Exactly that. And effectively, these are tensors that are the result of your computational graph, right? And they're no longer pixels. That makes sense?
I hope, yeah, I believe it did. So thank you very much for that.
Any other questions?
I don't, no, there are no other questions. So I think you've already touched on how they can get in touch with you. We've, of course, going to distribute this webinar recording in a follow-up email. So Sue, I don't know if you want to close it out for us.
Yeah, thanks, Chris, and thanks, Thomas. This has been great. It's a fascinating topic, and obviously lots of interest in this topic. We had a great number of people register who I'm sure will listen to the replay if they weren't able to be on live today. So in about 6 hours, those of you who are still on are going to get an email. It will contain a link to the replay. So if you want to kind of, go through here and look through any of this content and kind of reabsorb some of it. The other thing in that email will be a link to register for the next webcast, which is in 3 weeks. It's October 4th. And so please register for the next webcast. And thanks for coming today. Appreciate your attendance and hope to see you on another webcast in the future. Thanks, everyone.